Hello everyone. Today we're starting the proportional reasoning unit, and today we're going to be comparing and interpreting rates. So the two graphs below are Simon Whitfield's times for the 3 legs of the triathlons in which he competed during 2 different Olympic Games. The 3 legs of the race include a swim, followed by a bike ride, and finishing with a run. So the first thing we need to do is determine Simon's swim speed in both races. So the swim happens here and here. During the race in Sydney, at 0 minutes, he's at 0 kilometers distance. And then at 18 minutes 17 seconds, he's at 1.5 kilometers. So 18 minutes 17 seconds would be equivalent to 1,097 seconds. Because if we multiply 18 by 60, because there are 60 seconds in a minute, 18 minutes represents 1,080 seconds. So the total time to do the swim is 1,097 seconds. And looking at the Beijing race, at 0 minutes he's gone 0 kilometers, and at 18 minutes 45 seconds he's gone 1.5 kilometers. So similarly, we could convert 18 minutes 45 seconds into a number of seconds. 18 minutes again represents 1,080 seconds, and if we add 45 to that, we get 1,125 seconds total. So speed is given by distance over time, and very often these speeds are given in meters per second. So given the conversion 1 kilometer equals 1,000 meters, 1.5 kilometers would represent 1,500 meters. So Simon's speed in Sydney would be given by 1,500 meters divided by 1,097 seconds, which would be 1.37 meters per second. And his swim speed in Beijing would be given by 1,500 meters divided by 1,125 seconds, which would be 1.3 repeating meters per second. And now for his running speed, we need to examine this segment. So in this segment, the time goes from 77 minutes and 28 seconds to 107 minutes 24 seconds. So that would be an equivalent time in seconds of 1,796 seconds. Again, we need to do that because this is a weird hybrid unit with minutes and seconds, so we should get it maybe all to the same unit before we try to calculate the speed. And if we're going from 41.5 kilometers to 51.5 kilometers, the total distance ran is 10 kilometers, or equivalently 10,000 meters. So his running speed in Sydney is given by 10,000 meters divided by 1,796 seconds, and that gives us a speed of 5.57 meters per second. And looking at his race in Beijing, 78 minutes 10 seconds to 107 minutes 58 seconds would be an equivalent time total in seconds of 1,788 seconds. And again, if we're going from 41.5 to 51.5, that distance is 10 kilometers. And given our conversion here, 1 kilometer equals 1,000 meters, that's equivalent to 10,000 meters again. So now we can calculate his speed in Beijing. It would be given by 10,000 meters divided by 1,788 seconds, which gives us a speed of 5.59 meters per second. So the speed at which Simon swam and ran is called a rate. A rate is a comparison of 2 amounts that are measured in different units. Here's some examples of rates: 5 kilometers per hour, 120 words per minute, 42 pounds per square inch, $3.99 per 100 grams. So 3 of the rates above are called unit rates. A unit rate is a rate in which the numerical value of the second term is 1. So that works for this one, that works for this one, and this one, but not this one. So if we want to convert $3.99 per 100 grams to a unit rate, we just do $3.99 divided by 100 grams. So basically what we would do is type 3.99 divided by 100 into our calculator, and we would get a number of 0.0399. So in other words, our rate would be 0.0399 per gram. So in this next question, we're at the grocery store. One store sells a container of 650 grams of yogurt for $3.95, while another sells a 500 gram container of the same brand of yogurt for $3. And we need to decide which container is better to buy. So the first way we're going to approach this is by converting each to a unit rate. So the 650 gram at $3.95, we're going to figure out how many dollars per gram it is. So we're going to go $3.95 over 650 grams. We just type these numbers into our calculator and we get $0.00608 per gram. And for the other container, 500 grams at $3, we go $3 divided by 500 grams. And we type 3 divided by 500 in our calculator, and we get $0.006 per gram. So this container of yogurt is very slightly less expensive than the other container. This one requires a few more fractions of a dollar more per gram. So with our second approach, we're going to convert each to a rate with a common denominator. We'll maybe work on switching both to something per 500 grams. So the question we need to ask ourselves is, what do we need to multiply 650 by to give 500? So we can grab our calculators to figure out what the conversion factor should be here. In order to solve this equation, we need to go 500 divided by 650, and there's our conversion factor. I can store that as a letter. We'll maybe store it as A, and that's what I need to multiply the top and the bottom of the 650 gram yogurt rate to get it over 500 grams. So if I multiply the top and the bottom by the same number, the fraction retains its equivalent value. So if we go alpha A times 3.95, that gives us 3.04. And if we do the same to the bottom, alpha A times 650, that gives me 500, which was expected. So our new rate for the 650 gram container is going to be $3.04 per 500 grams. And now looking at this rate per 500 grams compared to this rate, it is again clear that the 500 gram container is a little bit better. For question number 4, it cost Jen $64.35 to fill her car with 55 liters of gas in Calgary. In Montana, the price per US gallon is $3.15 US per US gallon. The exchange rate is 73 cents US for $1 Canadian, and there are 3.785 liters in a US gallon. So is it cheaper to fill up in Calgary or Montana? So first we can look at Calgary. That's $64.35 per 55 liters. So we can make a unit rate out of that, and that'll be $1.17 Canadian per liter. And now we need to compare the gas in the US on the same footing. So we need to get it in Canadian dollars per liter as well. Now that's not the only way to do it, but as long as we're comparing apples to apples, we can figure out which is the better deal. So first we can start by converting $3.15 US into Canadian dollars. And knowing this exchange rate, we can figure it out. So we can start by writing 73 cents US is equal to $1 Canadian. And the trick is we need to arrange these into a fraction so we can cancel the US dollars. So I'm going to multiply 315 US by these numbers, and I'm going to arrange it so that US dollars cancels out, and we're left with Canadian dollars. So we know $1 Canadian, and this is 73 cents US. So when we do this multiplication, US divided by US is 1, and we're left with Canadian dollars. So in order to do this calculation, we do 3.15 times 1 divided by 0.73. And that gives us $4 and roughly 32 cents. So $3.15 US is equivalent to $4.315 Canadian. And next we need to convert 1 gallon into a number of liters. So given that there are 3.785 liters per 1 US gallon, we can multiply 1 gallon by 3.785 liters per 1 gallon, and gallon divided by itself is 1, and we're just left with a number of liters. So if we do 1 times 3.785 divided by 1, that gives us 3.785. So if we spend $4.31 Canadian for 3.785 liters of gas, that comes out to $1.14 per liter, and $1.14 Canadian per liter. So it looks like it's slightly cheaper to buy gas in Montana. One car manufacturer claims that the fuel efficiency for the Python car is 8.8 liters per 100 kilometers in the city. The Cobra car has a fuel efficiency of 11.3 liters per 100 kilometers in the city. So first, which car is more fuel efficient? So the Python uses up 8.8 liters of gas to drive 100 kilometers, and the Cobra uses up 11.3 liters. So the Python uses less gas per 100 kilometer distance traveled. In part B, Jen has one of the two cars stated above. She drives her car until it is almost empty of gas. She notes the odometer on her car states 12,789 kilometers. She fills her tank, drives for a week, and fills her tank again using 29.5 liters. The odometer on her car now reads 13,125 kilometers. So we're going to determine her fuel efficiency over the course of the week and see if that figure is closer to the Cobra's efficiency or the Python's efficiency. So at the start of her trip, her odometer read 12,789 kilometers. She drove for some time, and then it read 13,125 kilometers. So if we subtract this distance from the larger one, that gives us a total distance covered. So it turns out she drove 336 kilometers. And since she used 29.5 liters of gas to cover this distance, we can figure out her fuel efficiency. So we're going to go 29.5 liters divided by 336 kilometers. So that's going to give us a figure of 0.08779 liters per kilometer, which is a unit rate, and it's a little bit difficult at the moment to compare it to the fuel efficiency of the Cobra or the Python. So we can either convert the fuel efficiency of the Cobra and the Python as advertised to a unit rate. So basically we would type 11.3 divided by 100 and compare it to this number. And we would type 8.8 divided by 100 and again compare it to that number. Alternatively, we can convert her fuel efficiency experiment into liters per 100 kilometers so that we're comparing the same fuel efficiencies as advertised. So if we want to get her fuel efficiency into a liter per 100 kilometer, we just need to multiply the top and the bottom of this number by 100. And that leaves the overall number unchanged because we're basically multiplying by 1. And this gives us a fuel efficiency of 8.78 liters per 100 kilometers. So it looks like her fuel efficiency matches closer to the Python. So that's probably what she's driving. Looking at question number 6, Johnny lives in the Netherlands, where transportation for one trip often means using a bicycle, walking, taking a train, and a bus. The graph below shows Johnny's trip from his home to meet a friend. So we need to label each of the important points with letters and then describe a scenario, including the speed in kilometers per minute. So it's important to keep in mind that for a distance time graph, the steeper the slope, the faster it goes. So this would be a fairly quick speed, and something like this would be a little bit more gradual. So on this first leg, it's very likely that he was on a bike, and on this next leg, it's a little bit flatter, so it's probable that he was walking there. On this leg, it's fairly steep, and the trains in Holland tend to be quite fast, so it's probably not a bus there. For this leg, it's probable it's a bus, because it's a little bit flatter and a little bit slower. At this point, he's arrived at his friend's house, and he stays there until this point in time, and then it looks like he gets on a train and goes back home. And again, this leg looks a little steeper than the one over here, so it's probable that this was a bike. And now we need to calculate the speeds. Each one of these ordered pairs gives the time first and the distance second. So for this first leg, when he's on a bike, he goes from 0 kilometers at 0 minutes to 2 kilometers in 6 minutes. So his speed on the bike is given as 2 kilometers per 6 minutes. And if we do 2 divided by 6 in our calculator, we get 0.3 repeating kilometers per minute. For this next leg, he starts walking at 6 minutes and stops walking at 16 minutes. So if we do 16 minus 6, that gives us a time span of 10 minutes. And it looks like he's gone from 2 kilometers to 2.5 kilometers. So he's covered half a kilometer on foot. So that means his walking speed is 0.05 kilometers per minute. For the next leg, he gets on the train at 16 minutes and then gets off the train at 25 minutes. So his speed on the train will need to incorporate a 25 minus 16 minute time, and 25 minus 16 is 9 minutes. The distance he's covered on the train goes from 2.5 kilometers to 22.5 kilometers. So total distance here is 20 kilometers. And if you go 20 divided by 9, that gives you 2.2 repeating kilometers per minute. And now for his time on the bus, he gets on the bus at 25 minutes and gets off the bus at 45 minutes. So his speed on the bus is going to be 45 minus 25 minutes in total. So total time on the bus then is 20 minutes. And his distance covered on the bus goes from 22.5 kilometers to 34.5 kilometers. So if we go 34.5 minus 22.5, that gives us 12 kilometers. And then in our calculator, we do 12 divided by 20, which gives us a speed of 0.6 kilometers per minute. For this flat section, from 45 minutes to 105 minutes, he goes nowhere. He stays at 34.5 kilometers. So his speed while he's in the house, he covers 0 kilometers in 60 minutes. So his speed is 0 kilometers per minute. At 105 minutes, it looks like he gets directly onto the train. So it's possible his friend lives right next to the train station. And over the course of 20 minutes, he gets to where he's going on the train. Because we start at 105 minutes and we end at 125 minutes. During this time frame, he goes from 34.5 kilometers back to 2 kilometers. If we were to write the calculation for the speed of the train on this leg fully, we would go 2 minus 34.5 kilometers and divide that by 125 minus 105 minutes. Now 2 minus 34.5 would give us negative 32.5 kilometers. And if we divide that number by 20, we get negative 1.625 kilometers per minute. So what this means conceptually, with the negative there, it just means that he's returning home. Suppose he needs to travel north to get to his friend's place, and that would be positive. On this leg here, he's traveling south, so that's why the negative. And for the last leg of the trip while he's on his bike, he goes from 2 kilometers down to 0 kilometers. So we would do 0 minus 2 kilometers. And he does that in a time from 125 minutes to 131 minutes. So 131 minus 125 is 6 minutes. And we get a speed of negative 0.3 repeating kilometers per minute. And again, the negative sign just communicates the direction that he's traveling. The magnitude of this number just gives you the speed. So the last thing we need to do here today is convert the speed of the bus and the train to kilometers per hour. So the speeds we found for the bus, the train there, and the train back are all given in kilometers per minute. So we're part of the way there, but we need to know how many minutes there are in an hour to do this conversion. So in 1 hour, there are 60 minutes. So we're going to arrange this equation into a fraction so that we cancel the minutes. So for the bus, we're going to multiply by something, and we want to end up with kilometers per hour. So given that the hours are in the bottom, we should probably have hours in the bottom for our fraction. So that would be 1 hour in the bottom. And for the top number, 60 minutes. So with this, we basically just need to multiply 0.6 by 60, and minutes divided by minutes cancel, leaving us with 1, and we have kilometers per hour. So 0.6 times 60 gives us 36 kilometers per hour. And for the train going there, we multiply by the same fraction. We want to cancel minutes and be left with hours in the bottom. So minutes divided by minutes is 1, and we're left with kilometers per hour. So we need to do 2.2 repeating times 60, and that gives us 133.3 kilometers per hour. Now for the train going back, if we're just dealing with the speed, we can disregard this negative sign. That just gives us the direction. Again, we just need to multiply by the same fraction. 60 minutes up top, hours in the bottom. Minutes cancel out, and we're left with kilometers per hour. So 1.625 times 60 gives us 97.5 kilometers per hour. So to recap, in general, 2 or more rates can be compared by converting the rates to unit rates, where the numerical value of the second term of each rate is 1. Or, alternatively, we can write the rates so that the numerical value of the second term of each rate has the same value, like we did with the yogurts, comparing each price per 500 grams. The slope of a graph relating two quantities represents a rate of change of the quantities being represented. So that's it for me for today. I'll get you to do these questions in your textbook. This one for sure. These ones would be good for you to try out. I'll see you next time.